Math 31, we're going to take a look at example 2. And example 2 is going to take a while to unpack. It's really going to test you in terms of how well you remember certain graphs of functions. So we're going to practice these. You've got a linear function, a quadratic, down in part C you have a rational, part D you have a radical. And one of the main points of Math 31 is for you to be able to look at functions and their equations and get a general idea of their graph relatively quickly, along with some traits about their graphs. And two of the big traits we always talk about are domain and range. So we're going to practice that through 4 very different types of functions, but 4 functions that we'll be looking at specifically in Math 31. All right, so we're going to determine whether each relation defines a function, and then we're going to give the domain and range. All right, so taking a look at this, I hope this equation looks familiar to you. This is the equation of a line. We have y equaling mx plus b. So my slope here is 2, and my y-intercept is the ordered pair 0, -5. So at some point in your math careers, you've graphed a line. So let's go ahead, label and scale your axes. All right, so you see me labeling them x and y. And when I say scale, you're telling me what each square represents. I'm going to pick each square to represent 1 unit. So this is 1, 2, 3, 4, 5, so on and so forth. So it looks like my y-intercept is 0, -5. I'll start there because my y-intercept is my starting point. 1, 2, except I can't count to 5 right now. It is getting late on a Saturday night, or late for me. Okay, so we got 0, -5. All right, my slope is 2. Now, if I want to write that as a fraction, you can think of that as 2 over 1. So I'm going to rise 2, run 1, rise 2, run 1, rise 2, run 1. And then I'm going to draw in my line. I can see the shape of this line now. All right, so there we go. There's my line, 2x minus 5. Now, it passes the vertical line test. All non-vertical lines do pass the vertical line test, so this is a function. All right, oops, that's supposed to be a happy face. Now, in terms of the domain and range, keep in mind domain, we want to think about left, comma, right. Range, we want to think about down, comma, up, and we want to fill in whatever we can based on the graph. Now, if I look at the graph, I have some arrows. So let's talk about the direction of these arrows. This is right forever and up forever. This one over here looks to be, it's going down and left. So we're going to say left forever and down forever. And it's a little scrunched in. I don't have a ton of room to write that. Okay, but domain is left to right. So I see left forever to right forever. That's going to translate to all real numbers. -infinity to positive infinity with parentheses. Great. And then down to up, I do see a down forever and an up forever. So I also have all real numbers for my range. And most lines do have a domain and range of all real numbers. The exceptions are the horizontal and vertical lines. Okay, so we have that. Function, got the domain, got the range. Here we go with y equaling x squared plus 3. Now, y equaling x squared is one of your toolkit functions that we talked about at the end of section 2.7, or excuse me, the end of section 3.1, that you should know that y equals x squared is your basic parabola. Okay, I have y equaling x squared plus 3. So if you know how to graph that on site, fantastic. But let's say you don't. You're kind of like, well, I don't totally remember. Let me give you a technique that will always work. You can make your own little XY table. And I do this frequently enough. And I'll show you what I mean by this. So put X's here, Y's here. Typically, I'll pick my favorite 5x values, and I usually go -2, -1, 0, 1, and 2. Since x is the independent variable, you can pick any x values you want, and these are my basic 5. I don't always pick these. especially when we get into transformations. I might shift left or right a little. It just depends, but this is a good example to just plug in these 5. So let's plug in -2 and see what we get back out. -2 squared is 4. 4 plus 3 would be 7. All right, -1. -1 squared is 1. 1 plus 3 would be 4. 0 squared plus 3, 3. And then it should be symmetric because parabolas are symmetric. So with these 5 ordered pairs, let me get my graph going. Again, label is scale. So we've got -2, 2, 4, 6, 7 there. And then I've got -1, 4, and then it's symmetric, and there. Okay, I can see my parabola. Something like that. Okay. So now for domain and range, it's always our standard. We're going to go left to right, and we're going to go down to up. And let's see what we can fill in. I do see some arrows, so this one is going right and up. Let me scrunch this in here. This is going left and up. Okay, so domain is left to right, so we've got left forever, right forever. That's going to translate to all real numbers. Okay, and then we've got down to up. I don't have a down here. I do have an up forever, so I know at least the right endpoint is going to be positive infinity. Now down forever, I need to look at my lowest y value, right? So if I'm moving down to up, I finally hit a point right here. And the coordinate of that ordered pair, that vertex, was 0, 3. And again, if I were talking about range, I only care about that y value. So my lowest y value is 3. And because I want to include 3 in my range, I'm going to put a bracket around it. Okay? So I'm assuming you've graphed lines before and you've graphed parabolas. It's just a review for you, or hopefully a review. We'll practice these a little bit more as we move through the sections. Now the 2 that you might be less familiar with, that again, I'm going to assume you've seen, but it might have been a little while. Let me get these into view. Okay. There we are. All right, so taking a look at these, let me move this just a bit. All right, we're gonna run into some domain issues. Now, I'm gonna scribble this off to the side here because this, I've mentioned it before in this class, but it's gonna come up many times. There are 3 domain issues in math. All right, the first one is where you have a fraction with your denominator equaling 0. That's a bad sign, right? The second one is when you have an even index of a negative number. All right, so I'll put even index. Oops. Along with the negative radicand, which is fancy for anything under the radical. That is a problem. And then the third one is when you take the logarithm of a 0 or a negative number. All right, or we might say your argument is not positive. All right, so in terms of these 3 domain issues, I'm going to assume you've talked about these 2 before. And for some of you, you may have heard of a logarithm and talked about how your argument has to be positive, or another way of saying that is it can't be 0 or negative, or maybe you haven't. I'm not entirely sure. We will get into this in chapter 6, so that's coming. But I want to review these 2 ideas here. So in part C, you can see I have a fraction. So my little spidey senses go off. I'm going to have to pay attention to that. In part D, I have a radical. And that index is 2, right? I do have an even index, so I have to make sure that my radicand, my 5 plus 2x, is greater than or equal to 0. So I will have domain issues here. All right, so let's talk about how you find a domain issue when you have a fraction. Now, take a look at your denominator. The one thing you don't want is for this denominator to equal 0. So let's see when it does equal 0. So when is my denominator equal to 0? Well, if I subtract 2 from both sides, that will specifically be when x is equal to -2. Now, we haven't talked about this yet, but it is coming up. When you have a fraction, or what we'll call a rational function, wherever your denominator zeroes out, and only your denominator, you're graphically going to have a vertical asymptote. So what that means is if I scoot over to x equaling -2 and draw that vertical line, I'm going to dot it. It's like a boundary that your function won't cross. Okay. So I will have a vertical asymptote at x equaling -2. Now again, we will talk about this in much more detail at a later section, or in a later chapter, but I just want to give you a preview. And again, I'm hoping you've seen some of this before. Now, if you don't have any idea in terms of, okay, what does my graph look like? You can always graph some ordered pairs. I'm gonna try and squeeze it in here just because I'm running out of room. So let me make a little t-graph here, or a t-chart. Now, if I was going to do my 5x values like I always do, I'm going to run into some problems because I can't plug in -2. And I want to see what's happening on the left side of this, which happens to be -2. So I'm going to shift this just a little bit. I'm going to try, let's see, a little bit to the left of this. Let's try -4, -3, and then we'll do -1 and 0. Let's try those. So let's plug in -4. So -4 plus 2 is -2. 3 over -2 is -3/2. All right, if I plug in -3, -3 plus 2 is -1. 3 divided by -1 is -3. Let me plug in -1. -1 plus 2 is 1, right? 3 over 1 is +3. Let's try 0. 0 plus 2 is 2. 3 over 2, 3/2. Okay, so let me graph what I have. I have -4, -1.5. I have -3, -3. I have -1, +3, and I have 0, 3/2. Now, if you're experienced enough with these rational functions, it looks basically like a hyperbola. It's similar enough to your toolkit function that we talked about on page 174, which was the reciprocal function. So your basic graph looks like this. Okay. Now, if you're thinking, well, I don't know that I would have known that. We've talked about how you can graph these on your calculator. So I could head over to my y equals, clear out whatever was in there. It looks like the last thing I graphed was a cubic. I can do 3 divided by, and be careful, put your denominator in parentheses, it's a binomial. I'm going to hit zoom 6, and I'm going to see the basic shape of what my graph looks like, and that's pretty much what I have on my calculator, excuse me, on my graph here. It matches my calculator. And we talked at the end of section 3.1 about how you can use your table. So if I hit second in graph, I could get a whole bunch of ordered pairs. I mean, you see the ones that I did, 0, 1.5, 1, 1. Oops. Oh, we didn't do 1, 1, excuse me. We were on this side of things. We did -4, -1.5, -3, -3, -1, 3, and 0, 1.5. And you see your calculator actually saying you're not allowed to plug -2 into your function. So I've got my basic graph. Okay, that's all fine and good. Let's see if we can figure out domain and range. So again, I'm going to go left to right, and then I'm going to go down to up. And I've got a bunch of arrows. Okay, so let's take a look at these. If I go left to right, you can see that I have here a left forever, right? Okay, and this one isn't going up or down, it's just going left forever. Here I have right forever. Here I have down forever. And here I have up forever. So all of my forevers have been activated, but there's a catch. All right, let's talk about the domain. So as I move left to right, I have ordered pairs all through here, except there are none at x equaling -2, because -2 is not in my domain. I am not allowed to plug -2 into that function. So how we write that up in set notation is we say, well, we started from -infinity and we went to -2. We had to stop there, and I'm going to put a parentheses around it because I don't want to include -2 in my domain. But I want to start up just after -2 and go all the way to the right. So again, I am going left forever to right forever, right? I'm going -infinity to infinity, but we wanted to give -2 to the, give -2 the boot. We wanted to kick it out of our domain, and this is how we do it. We say, hey, go from -infinity to -2, this half of the xy plane, and then -2 to infinity. So we're basically throwing out x equaling -2. All right, for down to up, I see down forever, up forever. But maybe you're noticing on your calculator that I never pass this x-axis. And again, we'll talk at a later section about how I have a horizontal asymptote at the line y equaling 0, right? Vertical, x equaling -2, horizontal, y equaling 0. So I never actually cross the x-axis. So I go from -infinity to 0, and then 0 to infinity. And if you're wondering why I'm getting 0, because the x-axis is the line y is equal to 0. So I go from all the way down, but I never hit 0, and then I hop on the other side of 0 and go all the way up. So we never cross the x-axis, which is y equals 0, and we never cross x equaling -2. That's why you see -2 getting kicked out of my domain and 0 getting kicked out of my range. All right, one more. All right, these functions get just so much more fun to graph. Wait till they get even more convoluted. All right, so here we go. Now, here I have a square root, and I have to make sure my radicand is positive. So I need 5 plus 2x to be greater than or equal to 0. Now, we've solved linear inequalities before. So I'm going to take 2x, make sure it's greater than or equal to -5, or I'm going to make sure x is greater than or equal to -5/2. So when I go to make my little t-chart, and I'm going to put it down here, and I really can't do too many because I'm going to run out of space. All right. Okay, so I need to make sure my numbers are greater than or equal to -5/2. So I'm going to try and be kind to myself, and here's what I mean by that. I would like this radicand to be a perfect square so that when I square root it, it's a nice number. So if I think about perfect squares, I think the square root of 0 would be great if I could have it, or the square root of 1, or the square root of 9. And 9's ringing out to me because I can see if x is 2, 2 times 2 is 4, 5 plus 4 is 9. So I'm going to put a 2 here. That seems like a nice number to try. I'm also going to put, what could we put here to make this nice? What if I put 1/2, or actually specifically -1/2? All right, and you might be thinking like, where am I getting these numbers? I'm gonna show you in just a moment, or hopefully once we go through these, it'll become a little bit more apparent. And I'm also gonna try -2. So let me try those, and then also I'll try -5/2. And if you don't wanna try these, if you just wanna try 1, 2, 3, 4, that's great. And if you wanna use your calculator to assist you, that's great too. But let's take a look at why I'm picking these, okay? So if I plug in x being 2, 2 times 2 is 4, 5 plus 4 is 9, the square root of 9 is 3, okay? If I try -1/2, 2 times -1/2 is -1, 5 minus 1 is 4, and the square root of 4 is 2. If I try -2, 2 times -2 is -4, 5 minus 4 is 1, and the square root of 1 is 1. If I try -5/2, 2 times negative 5 halves is negative 5. 5 minus 5 is 0. Square root is 0, 0. So I picked these numbers specifically so that I could get nice integers back out. I wanted to see what would make my radicand a perfect square. So from here, let's see what we have. So I have 2, 3. I have negative 1/2, 2. I have negative 2, 1. And I have negative 5 halves, 0. Okay, it's looking something like that. Fantastic. Now this is also similar to your toolkit function we talked about at the end of section 3.1. This looks a lot like the square root of x, but it's just been shifted a little bit. All right, in terms of the domain and the range, again, I'm going to go left to right, and I'm going to go down to up. And let's see where this arrow is headed. This one is going right and up. So when I see right and up, I know I'm going to end with some infinities. All right, so now I need to find the leftmost point. Here is the leftmost point. Right, I found it. It's at negative 5 halves, 0, and I want the x coordinate from that, so I'm going to use negative 5 halves. I want to include negative 5 halves in my domain, so I'll put a bracket around it. So left to right, right? I start at negative 5 halves and I go to right forever. In terms of down to up, you can see my lowest y value is also at this same exact point, but now I'm interested in the y coordinate. So the lowest y value I hit is 0. And I want to include that in my range, so I'm going to put a bracket around it. Now, as we discussed again, towards the end of section 3.1, you can use your calculator to assist you with this. So let's say you were struggling with this. Start to use technology to guide your solution, right? I'm never going to take technology away from you. In fact, I want us to learn to use technology. I know we're just using the calculator here, but when you go into the real world, you'll use some form of technology. So let's go into our y equals. I'm going to write this as the square root of 5 plus 2x. All right, I'm going to hit zoom 6. And I'm hitting that zoom 6 just to reset my window in case I had a weird window from the last time I graphed something. So let's see. I can see the shape of what I graphed on my paper hanging out here. You have to be careful. You can see your calculator, at least, I'm not sure if it shows up on this video, but if you look close at your calculator, this graph doesn't quite hit the x-axis. That's because your TI-84 or TI-83 has some of the worst graphics ever. There's like 4 pixels total in this. So even though it looks like there's a gap between your function and the x-axis, you'll have to just know better and know that, oh no, that thing actually does touch the x-axis. And if you want to take a look at some of the table values, right, you can see that anything before negative 5 halves, which is decimal-wise negative 2.5, you see errors popping up. And then there you saw negative 2, 1, right? If I scroll to 2, you can see 2, 3 here. All right, you don't see negative 5 halves, 0 and negative 1 half, 2, because I haven't set the window to show you that. Not the window, excuse me, I haven't set my table. Let me do second in window. So if I wanted to start my window at negative 4, but I said, hey, calculate an x value, not every 1 unit, but every half a unit, then I'll get these two to show up. So now if I go to my table, you can see at negative 4 an error, negative 3.5 an error, but there it is. Negative 5 halves or negative 2.5, I hit 0. And if I go over to negative 1 half, there it is with 2. So the more you understand your calculator, the more you can make it work for you. All right, so with that, we're going to go back to where I give you the graphs, and then you tell me the domain and range. I'll see you in a few. Bye.